Greetings. We will discuss quantum tunneling today, and this is a very strange kind of phenomenon, which is why you see a subcaption here that facts are stranger than fiction. And the reason it would appear to be so is because of our prejudices and because of our conditioning to interpret physical phenomena in terms of our ignorance about the laws of nature. So, the laws of nature are deeper than what our everyday experience would suggest, which is based on classical considerations, but the actual laws of nature require quantum interpretation. And this is the consequence basically of the quantum uncertainty principle, the Schrodinger equation and the quantization, as we have discussed earlier. One of the classic examples of this very strange behavior is quantum tunneling and the explanation of the decay of the nucleus in which an alpha particle is emitted. And this was explained by George Gamow in the early days of quantum mechanics, 1929 I think, when Gamow explained this. So, Gamow is here. We will discuss Gamow's theory in this class. Gamow is here, and this is the laboratory of this is the Bragg laboratory. There are various other physicists in this image. And the background for this discussion is what we discussed in the previous classes, which is the Schrodinger equation for the time evolution operator, followed by the Schrodinger equation for the state vector, followed by the Schrodinger equation for the state wave function, which is nothing but the coordinate representation of the state vector. Now, this is the sequence in which I like to interpret the Schrodinger equation, and this is very much along the lines in which Sakurai discusses the Schrodinger equation in his book. And we have reconciled with the fact that for physical observables, there needs to physical observables need to be represented by operators. We can define this difference operator delta A in terms of the difference between the operator A and its expectation value in a given state, right. And this is what leads us to the uncertainty principle, and the uncertainty principle must be understood essentially in terms of these expectation values and difference operators and so on. So, this is the context in which we are going to discuss some applications of the Schrodinger equation, and in particular we will discuss the alpha decay. And what is strange about it is that the alpha particle, when it comes out of the nucleus, would need to overcome a very strong barrier, and that is a very non-classical phenomenon. George Gamow was a great storyteller, and he popularized science in a very big way. His book, several books, 1, 2, 3 Infinity is very famous. He got the Kalinga Prize, which was instituted by Biju Patnaik, and he got this award in 1956. The awards were instituted in 1952, and this is basically to popularize science and bring it to the people. The other applications of tunneling include functioning of the Esaki diode, for example, and then the scanning tunneling microscope. I will come back to this toward the end of this class, and this has really given rise to major technological advances, including nanoscience and nanotechnology. So, all this goes to a very fundamental idea that we are discussing today. So, although it looks very simplistic, it has got major applications. The applications go even in life sciences, and there is this classic paper by Perelov-Levine, who led the brilliant group of people like Yngve Owen, Jan Lindeberg, and so on in Sweden. And he talks about proton tunneling in DNA, and one of the ideas that is suggested in this, that this tunneling mechanism is part of the reason that is involved in aging processes. So, quantum mechanics impacts just about everything, including life sciences. So, what is common in physics, the idea that we are going to rest our discussion heavily on, is this equation of continuity that you see in this red box. You have seen this equation in fluid mechanics, you have seen it in electrodynamics, and it appears in quantum physics. So, on one hand you just have a flow of a fluid, okay, but then the same idea accounts for various phenomena in electrodynamics and then again in quantum theory. So, the enduring connections of these mathematical ideas in different branches of physics is a very beautiful connection between physics and mathematics, which we celebrate and use it to understand very subtle phenomena in physics. So, I begin this discussion with a commentary on the stationary states. So, we consider time dependence of expectation values of operators. So, we begin with energy eigenkets, which are eigenkets of such an operator which can be A, which commutes with H, which means that these are simultaneously observable. These are compatible observables. The corresponding operators commute, right, the energy operator and the other observable A, and eigenstates of A are the energy eigenkets, because they are these two operators can be simultaneously diagonalized in this basis. So, suppose you know the state at a time 0, which is the initial time, and then from this you can get the state at a later time t greater than 0, right. So, at a later time t greater than 0, you can get the state using the time evolution operator to operate on the state at time t equal to 0. And the time evolution operator is this, which involves the Hamiltonian for the system, and if you consider the initial time t0 to be 0, then it is just e to the minus I h t over h cross. So, this state vector at a later time is given by this, but you can expand this in a power series, infinite power series, and each vector will be an eigenstate of the operator operating on it, and you will get the eigenvalues, you will get an infinite series which will add up to this exponential function. Okay. So, if you now consider the expectation value of some other observable B, whatever, then the expectation value of this operator at a later time is given by the expectation value. So, you sandwich this operator in these states, and this is the time evolution operator from time 0 to time t. So, this will give you the state vector at a later time, and this is the adjoint of that vector. So, you are essentially looking at the expectation value of the operator B at a much later time. And as you can see from this, it turns out that from the time evolution operator operating on the state vector at time 0, you get e to the minus I e over h cross t, which is the time evolution dynamic phase, is the only thing that changes, nothing else, right. And these are scalars, these are just numbers, and they can move across, and the e to the plus I theta and e to the minus I theta over here cancel each other, and you essentially find that the expectation value at a later time is exactly the same as the expectation value at time t equal to 0, regardless of B commuting with H or not. The commutivity of B with H is not involved over here. So, the expectation value remains exactly the same, which is why these states are called as stationary states. Okay? So, the reason it is called a stationary state is because the expectation value of any operator at a later time remains the same, it remains stationary as it was at time t equal to 0, it does not change. So, that is the reason it is called as a stationary state. And notice that the time evolution of the stationary states is given by this dynamic factor. Okay, by this is the only change over time is this phase, which goes essentially as e to the minus I omega t, where omega is e over h cross. Okay. So, that is the phase how it changes with time of a stationary state. So, now if you take the coordinate representation of this state vector, you get the corresponding wave function. Okay. So, you can use either the Dirac notation or the de Broglie-Schrodinger wave function notation, and then if you consider the time dependent Schrodinger equation for this stationary state solution, then you can isolate the time dependence, because now you have to take the time derivative of this function on the left hand side. On the right hand side, it is only a multiplicative factor. So, on the left hand side, you get this time derivative, and when you cancel the common factors, you get essentially the time independent Schrodinger equation, okay, for the stationary states. Now, the time dependence of the stationary states is essentially given by e to the minus I e over h cross t, and we now solve this problem for a simple one dimensional potential. So, the first example we will consider is that of a step potential. The potential is 0 in the region x less than 0. So, you have got x axis, and the potential is flat, constant and 0 up to a certain point, and then suddenly it jumps up to a certain value v 0, and this is a simple one dimensional potential. Now, you can now set up the one dimensional time independent Schrodinger equation over here. So, you just write the Schrodinger equation, okay, and simplify this. So, I will not go through these details because it is very simple, all you have to do is to work it out. Okay. You manipulate these terms so that you can multiply everything both sides by minus 2m over h cross square, okay, and now bring this term, the energy term, from the right to the left. So, it comes with a plus sign, and now this is the equation that you have to solve. This is the second order differential equation that you have to solve, subject to appropriate boundary conditions. All the time dependence is there in the background, it is implicit, it is there in the e to the minus I e over h cross t. So, the potential in region 1, which is for x less than 0, is 0. So, the potential Vx is 0 in region 1, and in region 2, which is the region to the right of x equal to 0, you have a potential which is constant, which is V 0. Okay. So, this is these are the two regions of interest, and we have been using the subscript A until now, but we can drop it in subsequent analysis. and let us consider a solution corresponding to energy which is greater than the height of the potential. Now, this is the problem which many introductory courses on quantum mechanics do not emphasize. They emphasize the solutions for energy less than V0, but not always the solution for energy greater than the height of the potential. So, this is a very interesting situation. So, now let us consider the solution first for energy greater than V0, okay? And we write the potentials and energies in terms of these the constants k0 and k, which are just defined like this. So, E being greater than V0, E minus V0 is a positive number, okay. So, h cross square k square is also positive, all right. And when you put them, you can write this differential equation in terms of the k0 and k instead of E and V0, right. And the solutions have this general form. This is the general solution, e to the I k0 x plus r e to the minus I k0 x. So, you see that the first term in region 1, you have got two waves, one traveling from left to right and the other traveling from right to left. How do you know it is traveling from left to right and right to left? Minus? See, travel is always from a certain point to another point, and from a certain instant of time to another instant of time. Now, time is missing in this equation, but time is implicit in the equation. These are stationary state solutions of the time dependent Schrodinger equation. There is an explicit e to the minus I e over h cross t time dependence. So, you need to multiply all of these terms by e to the minus I e h cross I e over h cross times t, right, and then the phase becomes k0 x minus omega t, okay. The phase will then be k0 x minus omega t. So, what will be the surface of constant phase? K0 x minus omega t must be constant. So, k0 dx minus omega 0 dt will be 0, right. So, what is dx by dt? It will be a positive quantity and x will be increasing. For the second term, dx by dt will be negative and x will be decreasing with time, which is why it moves from right to left, okay. So, it is not just because of the sign, it is because of the relative sign, how this sign in the term involving space relates to the term involving time. So, there is an implicit time dependence which is e to the minus I e over h cross t, which is of importance here. In the region 2, you do have a solution moving which is a travelling wave moving from left to right, and now you know why it is travelling, because there is an implicit time dependence e to the minus I omega t, right. But there is nothing in the potential beyond it to send it back, and therefore, the coefficient of that component must be 0. So, in the region 2 there is only one term, okay. So, these are the solutions now, and we have energy greater than V0, and notice that R is not equal to 0 now. Now, this is really very strange. This should shock you, okay, because if you look at the classical analogues, all right, and I will show you a figure which will make it very clear. So, we have expressed these general solutions in terms of exponential a basis of exponential functions, but you can use any other basis. Any basis of linearly independent functions will work, but we have chosen traveling waves as the basis set, right. And the reason they are traveling is because of this explicit time dependence, which is e to the minus I omega t. Here also you have e to the minus I omega t. So, this is the phase, and this is the surface of constant phase for the first term will be moving from left to the right, whereas this one is moving from right to left. So, this is the reflected wave. Okay. So, the reason it is moving from left to right and right to left is with reference to the time dependence e to the minus I omega t of the stationary states. Okay. So, what is interesting is that there is a reflected component, and this has got absolutely no analog in classical mechanics, because if you have a roller coaster, you know what a roller coaster is. Okay. So, you go up and down, right, and if you have a situation in which the kinetic energy, you have got a roller coaster which is moving from right to left in this figure. This is the potential which has got a shape like this, right. And suppose the kinetic energy at the point P2, which is here, is less than the kinetic energy of at point P1. What would happen? You expect it to turn back, right. You expect it to turn back, you expect that it will not cross. But what if the kinetic energy at the point P2, if it is moving from left to right, is greater than the potential energy of the point P3? Then what do you expect the roller coaster to do? You expect that it will climb over and go. Now, that does not necessarily happen. It is most likely to happen, okay, but there is a component of the reflected wave, even when the energy is greater than the height of the potential. So, which is really very shocking, all right. So, there is a certain probability that the particle, even if it has an energy which is, so look at this step potential figure, you have got a particle which is incident from the left and it comes at an energy which is greater than the height of the step, right. So, E is greater than V0, but the reflection coefficient R is not 0. So, this is the most general solution as we have seen. So, this is coming from mathematics, but it is telling you something which is very strange. So, it is counterintuitive only because of our prejudice, because we tend to think in terms of classical ideas, but here you have R not equal to 0, there is no reflected wave in the region 2 because there is nothing to reflect. So, that part I have already discussed, but that there is a reflected wave in region 1 is strange enough. It is a completely quantum effect, all right. And this is how the real law of nature operates. So, it is not the laws of nature are different for classical mechanics and different for quantum mechanics. There are only one laws of nature which are quantum mechanical. Classical laws are only approximate and they are not correct. Okay. So, that is the reason Niels Bohr says that if quantum mechanics has not profoundly shocked you, you have not understood it. Okay. So, this is really an amazing result. So, there is an optical analog, because light also means it can get partially reflected, and particles also, electrons and particles and other objects also follow the same type of rules, which is why Feynman says that electrons behave in this respect in exactly the same way as photons. They are both screwy, but in exactly the same way. Okay. And this is the manifestation of the wave particle duality, all right. So, you have got this classical phenomenon which is beaten by the laws of nature, which are correctly described not by classical mechanics, but by quantum mechanics. And now we consider the other case which is more commonly discussed in most books and courses on quantum mechanics, which is the case when the energy of the particle is less than the height of the barrier. So, here again something strange is going to happen, and you set up the Schrodinger equation for the two regions by recognizing what the difference between the energy and the potential is. So, the first region the potential is 0, in the second E minus V 0 will be negative. Okay. So, you can write this, the square of k is negative. So, you can write k, which must be an imaginary quantity, in terms of I kappa, where kappa is real and positive, okay, and then do this analysis in terms of k and kappa. So, now you have the Schrodinger equation for the two regions 1 and 2. Again you write the most general solutions. So, in region 1, as before, you have an incoming wave as well as a reflected wave. In the region 2, there is a transmitted wave, but there is no wave moving from right to left, all right. But the transmitted wave is not a traveling wave, because the coefficient now, the phase is I k x, which is e to the minus kappa x. So, it is going to be a damped amplitude, it will get exponentially damped. Okay. And because it is exponentially damped, the probability density on the other side will be non-zero to a certain extent till the damping is complete, which will happen only as x goes to infinity. But what is interesting is that there is a certain probability density outside, but it does not necessarily mean that okay, that the particle has physically penetrated and moved away into the region 2, because that is something you have to determine in terms of the current density vector, which I mentioned earlier, that the current density vector and the equation of continuity involving the del rho by del t, which is 0 for stationary state. So, the divergence of J must vanish, it is a solenoidal vector, and in terms of the current density vector is what we should now carry out this analysis, and it gives you shocking results. Okay. So, you see that t is not 0, there is a certain probability amplitude which you can find in the classically forbidden region. So, let us look at these solutions now, and we have to interpret these solutions in terms of the current density vector. Okay. So, the equation of continuity is satisfied, the current density vector is defined like this, and when you are dealing with stationary states, the del by del t of psi star psi goes to 0, and therefore, the divergence of J is 0. So, you have a solenoidal current density vector, and in terms of this we get some very strange results, which again are very surprising and counterintuitive. So, no wonder that Feynman says that nobody understands quantum mechanics. But of course, Feynman is one of those who has explained it to everybody. So, here we have these two different situations, one, and both are strange, one in which the energy is greater than the height of the barrier, but there is a reflection, the other in which case the energy is less than the height of the barrier and there still is penetration, and both are in some sense absurd ideas. So, this is the quantum world in which we live, and one needs to follow the mathematics. Okay? And Dirac points out that if you are receptive and humble, mathematics will lead you by the hand and you follow the mathematics. So, mathematics is so intimately engaged with the laws of nature that you trust mathematics, go with it, and it will lead you to the correct interpretation. So, which is what we will do now. So, we consider the first case E greater than V0, we have the solutions that we have written earlier. You have the boundary conditions, okay, the wave function and its derivative must be continuous. If it is not continuous, if the wave function is not continuous, you cannot define the first derivative. If the first derivative is not continuous, you do not have the second derivative, and if you do not have the second derivative of psi, you do not have the Schrodinger equation. Okay? The Schrodinger equation is a second order differential equation. So, obviously, the function has to be continuous. So, this is not a separate postulate or anything like that, it is built into the framework of the second order differential equation, which the Schrodinger equation is. And if you apply the boundary condition 1 that the wave function must be continuous and its derivative should also be continuous, then you get these two relations 1 plus r equal to t, okay, and I k 0 1 minus r equal to I k t. So, you can write these boundary conditions and get r and t in terms of k and k 0 and discover that t and r are both not 0. So, t not being 0 is what you would expect, but r not being 0 is what you would not expect from your experience on the roller coaster. Okay? So, you have got the reflection amplitude and the transmission amplitude. The interpretation in terms of the current density vector, and you can write the current density vector for the incoming wave, for the reflected wave and for the transmitted wave, and from their ratios you will get the reflection coefficient and the transmission coefficient, okay, because they represent the current density vector j dot delta s will give you the flux. Okay. So, how much flux comes in and how much is reflected and how much is transmitted will come from the current density vector when you consider j dot delta s. So, you determine the reflection coefficient and the transmission coefficient from the ratios of the reflected flux to the incoming flux and the ratio of the transmitted flux to the incoming flux. So, you have this very interesting relationships which will remind you of the ratio of the speeds, okay. The ratio of the speeds in vacuum and the ratio of the speed of light in medium is nothing but the refractive index, and you have got a similar quantity over here, and you can find the reflection and the transmission coefficients which are complementary, and you find that this is a very non-classical counterintuitive result that you get from quantum mechanics. So, this is the summary of what we have got so far, and now we discuss an interesting situation here, that you have the modulus of t square which is not 0, okay. But then the modulus of r square is 1. Now, this is again very strange, okay, which means that there is no net flux transmission. If the energy of the particle is less than the height of the barrier, there is no net flux transmission. Probability amplitude is by itself is not flux, okay. Flux is something that you get from the current density vector, which is a different thing than the probability amplitude itself. Okay? So, the fact that modulus of t square is not equal to 0, but the modulus of r square is equal to 1 is a very strange result, because if you look at the flux, there is total reflection. Okay. But for that you have to look at the flux and not just the coefficients of the amplitude coefficients of the corresponding wave functions. So, what you have on the right side across the potential barrier in the non-classical region is an exponentially damped wave. Okay? It is called as an evanescent wave. Evanescent means like it is there, but it is not there. Okay? So, there is no classical analog for that. All right? It is evanescent, it is there, but it is not there. It is there because you have got a coefficient t which is not 0, but it is not there because the reflection coefficient ultimately, when you consider the flux, turns out to be 1. So, everything gets totally reflected. So, this is an awesome result in some sense, and maybe even an awful result, right. So, if you look at the probability density in the region 2, it decays exponentially, all right. And you understand it by considering the probability current density vector J. So, Jx will turns out to be 0, okay, and then everything falls in place. So, you need to carry out this interpretation in terms of the current density vector. So, now we can ask another question. You have got this step, right, and in the non-classical region, in the forbidden region, you have got an exponentially damped wave. So, the exponentially damped wave, it does not cut off sharply at the step potential, but over a certain distance. Now, before it goes to 0, if the step potential is cut and it drops to 0, what would happen? So, now you have got a probability density, okay. You had total reflection when there was a step potential and it stayed like that all the way to x going to positive infinity, right. But now the potential is not going to be the same up to x tending to infinity, but before this exponentially damped wave goes to 0, it cuts and falls to 0, and this thing has already escaped. Now, this is tunneling. You get it? So, let us see how that happens. So, the potential, so this is a step potential, but now it does not remain constant up to infinity, but before this thing has dropped to 0, it cuts. And so, we will take a simple rectangular barrier potential, and now what we are going to find is a tunneling effect. Now, you have to be careful about the term tunneling, because in some sense it can even be misleading. Like when you are going and you are crossing a barrier, then what do you expect? When will you be able to cross a barrier? Means if some of you have done horse riding and jumped hurdles, which is really great fun to do, you go on the horse, right, and you have got a barrier, and the horse has great reflexes, so it sees the barrier and it jumps over the barrier, but it needs energy, it needs sufficient momentum so that it can overcome the height, right. The other way it can go across a barrier is through a tunnel as you see over here, which is to dig a hole into the mountain, right, into the barrier, and then go through it. Now, both of these are classical pictures. The quantum tunneling has got absolutely no classical analog. It is not tunneling by digging a hole. Okay, we are using that term. It does not mean that it is like making a tunnel and going through it. So, it has got some analogy over there, but then it is not complete, and it is important to recognize the similarity, but also the difference. Okay? There is absolutely no classical analog to quantum tunneling. So, the term has to be used with a certain care, and you have this potential barrier. So, I will again here you recognize that you have got these two solutions, incident wave and a reflected wave over here, and a transmitted wave, but there is no component moving from right to left because there is nothing on this side to send it back. So, you can apply these boundary conditions and then solve the Schrodinger equation with appropriate boundary conditions of continuity of the wave function and its derivative at the boundaries. So, I will not work out these details, but I am going to share this PDF with you so that you know you will be able to work it out, but it is best that you do it yourself. So, I will quickly demonstrate the major steps that you set up the Schrodinger equation for the region 1, this is a region 1, this is a region 2, and this is region 3, and you set up the Schrodinger equation for the 3 regions, and then get your solutions in terms of the k and kappa. Okay? So, now this energy is less than the height of the barrier. So, E minus V 0 will be negative, and that is the reason you introduce this I kappa term here. So, you can work it out if the analysis goes along similar lines as we have done in the previous exercise. It is just a matter of details, work it out, but I will not spend much time on this, and you find that the transmission coefficient now is not 0, and you actually have a flux which has penetrated through the barrier. Okay? In the previous case there was no net flux, in this case there is, all right. So, you can get these coefficients R and T in terms of the k and kappa, and discover that there is a net flux which is a result of the quantum tunneling, and you can write these solutions in various alternative and equivalent mathematical using functions, and find that this tunneling probability goes as e to the minus 4 kappa a, but I will write it in terms of d. D is the barrier width. Okay. So, d is twice a. Okay. So, this tunneling probability goes as exponentially it reduces with kappa, which is the difference in the energy between the energy and the energy of the particle and the potential itself, and also the width. So, larger the width, the lower will be the probability, and so on. So, you have this important result that the tunneling probability reduces exponentially, but it is not 0, and that is the important thing, that it can diminish, but so, and since it goes as e to the minus 2 kappa d, you can take its logarithm which is proportional to d, the proportionality is kappa. And if you now have a potential barrier which is not just a rectangular barrier, but it has got some arbitrary shape. So, if you consider this barrier of arbitrary shape, you can slice it into rectangles of this type and then solve the corresponding Schrodinger equation for each rectangular strip using just the methods that we use, and in the limit you can let the width go to 0, so that you get a continuous function. Now, this is the trick which Gamow used, as I will show now. So, this is the method which falls in the spirit of what is known as the WKBJ approximation, when the potential is varying somewhat smoothly, okay. And essentially you have this logarithm of t square which goes as minus twice kappa d, but you now have to add it up over all of these rectangular slices. So, you will then get logarithm of tau, which is the net probability of transmission, which is a sum of these corresponding terms for each slice. Now, this is the trick which Gamow used in the interpretation of the alpha decay. So, alpha decay, you know what alpha particles are, means these have been known from earlier times, from the Rutherford scattering experiment is well known, and these pictures give you some idea that okay, you have got a central nucleus which is a very tiny quantity of the order of 10 to the minus 14 meters, all right, and then you have got an atom. But I always like to caution you that these cartoon pictures of electrons going around this are very misleading. There are no orbits in quantum mechanics, all right. So, do not trust these cartoon pictures too much, but they are certainly useful in getting the basic idea that okay, you have got a central nucleus which is positive, and from this nucleus, the nucleus of uranium 238, which is a radioactive nucleus, an alpha particle decays by itself. It is a spontaneous decay, and it comes out with a certain energy. You are left with a daughter nucleus which is thorium 234, and an alpha particle comes out. So, how does this happen? How can it happen is a mystery, because inside the nucleus the alpha particles which are made up of neutrons and protons, they are very strongly attractive, they experience strong attractive interactions inside the nucleus, and the total binding energy of 2 neutrons and 2 protons is something like minus 24.4 MeV, which is over here, and when the alpha particle actually comes out, it comes out with an energy of about 4.2 MeV. And the potential outside the domain of the nucleus, outside this nucleus, this is the nuclear radius 7.75 Fermi, right. There will be a Coulomb repulsion, right, because the nuclear charge, which will be Z minus 2 because 2 protons are gone with the alpha particle, right. So, Z minus 2 into 2E divided by 4 pi epsilon 0 r in SI units, that is the nature of the potential. So, the nature of the potential, it is repulsive over here and it is attractive over here deep, and the alpha particle will need to hit this barrier and come out over here. Okay. So, this is the decay mechanism, and this was explained by Gamow using the quantum tunneling that we just discussed. What he did was to consider these rectangular barriers over here, one, another one, all right, and then you can divide any shape into small rectangular strips and let the width of the strip go to 0. So, essentially this is the potential that Gamow considers. So, this is just the Coulomb repulsive potential of the daughter nucleus, right, and here is an attractive potential. And if you consider many of these rectangular barriers, then Gamow explained in this paper in 1929, and essentially he used the same result that we got in the previous just a few slides prior to this, and he writes this logarithm of this t square in terms of this gamma, which is nothing but this integral from region A to B, where A is at the surface of the nucleus and B is where the Coulomb repulsive potential will become equal to the energy with which the alpha particle decays, right. So, which is about 4.2 MeV. So, this is the integration that can be carried out, and Gamow wrote this is a matter of detail, and he wrote this in terms of this rho, which is the ratio of A over B. But the basic idea is what I wanted to discuss, which is the tunneling mechanism which Gamow used to get this amazing result. Okay? So, the probability for an alpha particle to tunnel is given by this, but then this probability is actually enhanced, because here again this is a nice exercise in recognizing how physical models are developed, okay, because the actual decay mechanism is extremely complex and a very quantum process. But you can come up with some approximations, you can come up with some building models, and this is how difficult problems are solved. And this is a great example, because what Gamow recognized is that if it is coming out with a certain energy, and if it had a certain energy in the well, in the attractive well, then you can think of it oscillating between the walls of the well. And if it is oscillating, then the number of times it hits the wall per second, if that number is larger, then the probability of tunneling through will also be larger. If it hits that wall only once, it has as much chance as we have just now estimated. But if it is going to hit that wall many times, then it is going to augment its chance of penetrating. Okay? So, what he did was to estimate the characteristic speed of the alpha particle inside the nucleus, and this speed he estimated from the energy of the alpha particle, which would be its kinetic energy, and this if you consider the radius of the nucleus to be a, then the speed would be distance over time, and that gives the frequency at which the alpha particle hits the surface, and the probability p that you got, this probability which is t square, this probability will be augmented by this factor. Okay? So, that is what I refer to as probability of decay per unit time, which is p tilde, which is augmented from p by the factor 1 over r, which you are getting from this frequency. Okay? And when you put in this factor, you can estimate what the probability of decay per unit time will be. So, this you can connect with the radioactive decay rate, because the radioactive decay rate depends on the number of the radioactive species, and that rate is going to be augmented by this frequency. So, you have dN by dt equal to minus n, which is the usual radioactive decay relationship. The solution obviously will be an exponential function, because whenever you have a rate of change which is proportional to the quantity that is present at that instant of time. The solutions are always exponential. So you put this dN by dt equal to minus n times the probability, which is t square augmented by the frequency, and by putting this factor in, you can easily determine the solution, which is an exponential solution. You can find in how much time the total number of radioactive atoms would have decayed, find the half-life, and this is how the half-life of radioactive decay is calculated. Okay. So these problems are now quite easy to solve. You see that the half-life is given by this expression. If you take its logarithm, you can write it as a sum of these terms, okay, and you can write it more fully if you like, and this is the kind of solution. These problems are of current interest. This is a paper from just a few years ago, about 5 or 6 years ago, in Physics Letters, volume 734, in which many of these studies are carried out. So this is not just an old beaten up problem, these are problems of current interest, and you may want to acquaint yourself with current literature on these problems. So this has led to many fascinating applications, and Gerd Binnig got the Nobel Prize for the scanning tunnel microscope, which is an idea which is essentially based on quantum tunneling. It is nothing but the particles going past tunnel. So you have got a certain potential barrier between the tip of this tool and the sample surface, and electrons can actually tunnel through this barrier to generate a current, and this is what people use for surface analysis and to get details about the structure and so on. So this is why Feynman predicted in 1959 that there is his famous talk, which is known as plenty of room at the bottom, that the principles of physics, if they are properly manipulated, can lead to some very fascinating applications. And he imagined that, okay, this will actually make it possible to pick up a single atom, move it around and place it where you want. So what amazing control you can have at an atomic level, so that you can generate quantum electronic devices. Okay, and this was actually achieved in 1989 when IBM scientists, they picked up xenon atoms one by one and took 35 xenon atoms and placed them where they want to spell the letters IBM on a substrate which was chilled nickel crystal. Okay? And here is another image made by similar technology of carbon monoxide molecules. 28 of these carbon monoxide molecules were rearranged individually. Just think of, I can pick this up and move it wherever I want, but think about, picking up an atom of xenon or a molecule of carbon monoxide and placing it where you want it to generate a picture. Here a molecular man has been prepared, and this is all coming out of the vision in Feynman's lectures, or Feynman lecture of 1959, in which he said that I would like to describe a field in which little has been done, but in which an enormous amount can be done in principle. How do we write small? And see how small IBM has been written here. And this is all based on the simple phenomenon of quantum tunneling. Thank you. If there is any question I can take.
Um, Sir, in case of alpha decay, there is tunneling is happening.
Yes.
But what is happening in case of beta decay? Is it a similar kind of tunneling?
No, beta decay it is because of a weak reaction. So, there are nuclear interactions. So there is an electroweak interaction. So if you think about the fundamental interactions in nature, you think about gravity, electromagnetic, nuclear strong and nuclear weak. So what is responsible for beta decay is the nuclear weak reaction, and that subsequently in the work of Glashow, Salam, they unified it with quantum electrodynamics, and that becomes the standard model of physics. So there the mechanism is because of the physical interaction which is involved, which is the nuclear weak interaction, but which is now unified with the electrodynamic. Any other question?
Sir, page number 133, the binding energy of 2 neutrons and 2 protons is equal to negative 24.4 mega electron volts. But binding energy is positive always, right?
No, no, no. See, 0 and positive and negative, it has to do with your reference level. Okay, the kinetic energy is positive. It comes out with a kinetic energy of 4.2, right? Inside the nucleus, it is in a bound state. Bound states are always negative, like the energy of the 1s electron in the hydrogen atom. It is about minus 13.6 electron volt or minus 1 Rydberg. Why is it minus? Because to get that electron out, you have to give that much energy to pull it out. If this was a classical particle, you would need to give energy to pull it out. So it is minus. Any other question? What you have to give is positive, but the energy of that particle itself is negative.